Hello, everybody. I don't know, no one's quite listening yet. But anyways, these are going to be the office hours for Introduction to Agent-Based Modeling, the Complexity Explorer MOOC version of it. And we will be talking about any questions you might have and discussing what's going to be going on with the class and anything that happens along those lines. So anyways, the way this is going to work is that I'll take questions and then from either the Q&A app that's part of Google Hangouts, or if they are submitted on Twitter or email ahead of time, I'll also check those as much as I can. Right now, the course seems to be running pretty well. I do have a couple of just brief kind of record-keeping notes. So Unit 1, right now, sections through, I think it is 1.6, I'm double checking real quick, are up and live online. 1.7 are up and live online. 8, 9, 10, and 11 will be coming online shortly. Most of the units are only divided into 5 subunits, but this one, because it's the first week of the class, will actually first 2 weeks of the class will actually be 10 subunits plus a unit for review and testing. The next Unit 1 test won't be available until after until the end of the 2-week period. At that point, I'll make it postable. Now, the tests, just so you know, you only get one shot at. The quizzes you can take as many times as you want, but the tests you get one shot at, and it's the test that's used to determine your certificate at the end. So make sure, so part of the reason why I'm delaying the release on that is just to make sure that you have some time to go through all the videos and everything like that, and you don't try and rush right into it. Unit 2 will be released on August 15th, roughly 2 weeks after the first unit. And then after that, the next 8 units will all be released on a weekly basis. So 2, 3, 4, 5, 6, 7, 8, 9. There are 9 units in total. Do want to mention there's been a couple of small problems. For instance, some people have been having issues with the tuition window coming up right away, even if you've already paid your tuition. If you've paid your tuition, no reason to pay it again. You can just hit the skip button and it'll take you right on to the next set of lectures. We're working on the web platform, and theoretically that won't show up in the future again. So hopefully that will be fixed in the near future. We also had a couple of small, well, actually just one small bug in one of the quizzes where one of the answers wasn't set in quiz 1.4. So if you took it before and you didn't get an answer, that was because there was a small mistake. If you take it again, it will be fine. The other thing to mention is that, and the other thing to mention is some people have been reporting a small bug in the first quiz, just that the answers are already showing up. We're looking into that. We'll try and make sure we get that fixed right away. But the quizzes are there just for practice anyways, just to kind of give you some idea. So if the answers are showing up, that's not the worst possible part of the world. Finally, I did also want to mention that there is to go ahead and download NetLogo if you haven't done so already. You didn't need to have it necessarily to get the answers right away, but you should go ahead and install NetLogo because we're going to be using it quite a bit when we get to week 2. And I see that it looks like some of our participants have joined. So I think that's Sebastian and Paula. So hello, how you doing? Here, you're on mute right now. I gotta flip you off. Hold on, give me a second. Let's see, hopefully I can do this. Sorry, new technology. Oh, it seems your microphone isn't working. Oh, okay, so I see. So yeah, great to be here. If you have any questions, let me know. I was just kind of running through kind of all the stuff that's happened in the first week and everything along those lines. But yeah, let me just briefly mention how the office hours are going to work, right? So office hours will be at this time every week on Tuesday, so it's 11 a.m. on the eastern coast of the U.S., 10 a.m. in the central. But it varies from wherever your time zone is. I tried to pick one that would work for the vast majority of our participants. Hopefully it works out okay, but because people are spread all over the globe, it might not work out for everyone. But if you want to be an active part of the office hours, then feel free to email me ahead of time. I can actually add you in. Of course, you can always view the office hours. Oh, there you are. Okay, so oh. So yeah, so then you can actively participate. And we can have a more ongoing discussion if you email me ahead of time. Otherwise, all the office hours are recorded to YouTube, and I will post a link to them probably in the forums afterwards. So they're always captured and recorded there. Okay. Sebastian and Paula, did you have any questions, or were you any comments on the first unit? How's it going? All right. Oh, is your mic not working again? I can't seem to hear you. There. Oh, almost heard you. I mean, feel free to type in any questions if that works better. Sorry, that doesn't seem to be working. But just a quick recap, by the way, of other things going on. There was a small error in the quiz 1.4 where one of the answers wasn't mentioned. I think I fixed that now. So if you go back and retake quiz 1.4, you should get the answers correctly. Also, Unit 1, most of it should be up this week, and that will cover us through August 15th, essentially. Sometime around August 15th, I will also release the Unit 1 test. I'll hold off on the Unit 1 test until after 2 weeks have passed, just to kind of give people a chance to walk all the materials. Unit 2 will then be released around August 15th, and after that, it'll be on a weekly basis. So the other problem that a lot of people were mentioning questions about was just the fact that they were seeing the tuition page, even if they'd already paid their tuition. That's something we're working on. We'll probably get that resolved, but there's no reason to pay the tuition again. Just because that page shows up doesn't mean you haven't paid. Okay. So I did have a couple of questions that were submitted ahead of time, and I'll go ahead and start going through those. And Sebastian and Paul, if you have anything you want to add in at some point, you can just type it in as a comment if you want, or you can also, anyone can use the Q&A app and the Hangouts to submit a question. If you're watching on the YouTube stream as opposed to on the Hangouts chat app, then probably the best way would be to tweet about it with the @intro to ABM in the tweet, and that way I can pick it up pretty easily to see what's going on. So that should work. So the questions I had submitted ahead of time, one was basically if you received, for the lucky few who actually received a scholarship, right, does that include all the questions? And does that include all the units and materials? And yes, it does. So scholarship, this is, even if you pay the tuition, no matter what, you receive a scholarship, then it covers the entire unit, not the entire course, not any of the particular units. So you will be covered throughout the entire course for that. So that was from Martha Castellanos. So no worries. Once you're paid for the whole unit. And I think I just saw that Paula and Sebastian had a question. So Sebastian says, I've got a question. In the Walensky video, he mentioned that a little more density could cause a big difference in how many trees got burned. How are those thresholds determined and why do they occur? Great question. Very good question. So, this threshold is not automatically determined within the model, right? It's an emergent property of the outcome of the model, right? So essentially, it depends upon how the model is actually configured, how you put together the space. In this case, the answer turns out that you can actually solve this with a set of equations, but that's not always the case. It just happens to be the case here. And those set of equations basically say that for a two-dimensional world, right, this threshold is going to occur somewhere between the 57 and 62% density. Now that's I can post a link if you want to some of the actual analytical work on that. In reality, for a vast majority of agent-based models, they're too complex to solve using a set of equations. And so instead, these thresholds tend to be determined by running the parameters for different values many, many times, and then analyzing the results of what comes out of that, right? So in fact, we will talk about this later on in the course, and probably somewhere around Unit 6. I don't know, I have to look back at the course notes, but we'll talk about how to analyze the results of a model. And one thing you could have done with the FIRE model would be to run what we call a behavior space experiment, which allows you to manipulate one of the parameters slowly over time. And then you can basically run the model many, many times for each of those values of the parameter. And then you can graph what percentage of the trees burn. And for the FIRE model, it's going to look something like this, right? Where there's going to be very small percentage, very small percentage, very small percentage. And then you hit a point, and at that point, sometimes called a tipping point or a phase transition, right? All of a sudden, you go from a small percentage of the trees burning to a high percentage of the trees burning. So why do these occur is the second half of the question, right? And that's a very difficult question to answer. A lot of times it happens because of a bunch of nonlinear actions within the system, right? In the FIRE model in particular, it turns out that at that particular density rate, there is the probability that a single stream of connected green trees going from the left side to the right side of the screen goes to 1 at that rate, right? And it's just a matter of probabilities. You throw down a bunch of random trees, and as you throw down those those trees again and again, at that rate around 59 to 60%, all of a sudden the probability of that continuous line of green trees goes toward 1, right? In what was I going to say? In relation to that, right? There's also the question as to why. So let me take a step back. It's actually not necessary for the density to be at 59% or 62% to go from the left side of the screen to the right side of the screen. It's not 100% necessary. And you could think about this if you were just to think about it, right? So if you take the world, right, and the world in this case, actually, I can bring up the FIRE model and share it with you. That might be an interesting way to do this. Let me do that real quick. So coming up, give me 1 second here. So if you were to bring up the world of the FIRE model and you were to lay out the trees exactly the way you wanted them to be, right, rather than having them be randomly showing up in the world, you could lay them out straight from the left to the right edge of the world, and the FIRE would go straight across without stopping. And but this is at a much lower level of density than what would happen if you just laid them out randomly. And let me just load it up. Got it up now. Okay. And then I can share the screen with you guys. Give me a second here. Okay. So now everyone should be seeing the fire model. You see it there? Okay, good. So what I want to point out is that if I right-click on the background of the world in NetLogo, or if I control-click on a Mac, I can go to Edit, and we'll talk about this right at the beginning of Unit 2, actually, right? And this shows you what the size of the world is, right? And so in this particular case, the size of the world is it's actually 251 by 251 squares, right? So in reality, if you wanted to burn a fire from the left side of the screen to the right side of the screen, you would only need 251 trees, right? 251 divided by 251 times 251, which is the density, is only 0.003 density, right? So it's possible to create a density, a world in which the fire burns straight across, right? But it turns out that if you just plunk down the trees randomly, if you just put them randomly, you need a much, much higher density, something around 62%, in order for the fire to get from the left side of the screen to the right side of the screen. Right? So as I said, this is a result of kind of the way random probabilities work, right? In this particular case. But the more general question of why do phase transitions happen really depends upon the system. And it's a very hard question to answer. And it depends upon the interactions of the different particles and the different parts of that system. And we'll explore many, many occasions of that, right? And how that works within within agent-based model. Great question though, Sebastian, for sure. And Paula, thank you. Okay. Yeah, okay. So let me see that. I have one other question that had gotten submitted beforehand. Yes, so this is from Norman Rodriguez. And he had asked the question, what is the difference between agent-based modeling and systems dynamic modeling, and how can we integrate them? So for those of you who don't know, you should know what agent-based modeling is by now, hopefully, because we've talked about it. But systems dynamic modeling is another framework that essentially tries to explore how complex systems work by looking at components at the aggregate level. And there's some great work that's been done in this space. The modern proponent of it is a guy named John Sturman, who's at MIT, does some great work, and has written a piece of software. Well, and the piece of software that he often uses and that is best in this space is a piece of software called Stella that's used for system dynamics modeling. And the big idea behind, and so let me pull up quickly, let me stop this screen share and I'll pull up another one. So I just kind of want to show you quickly what systems dynamic modeling sometimes looks like, right? So this is actually the Wikipedia page on system dynamics. And as opposed to agent-based modeling, where systems dynamic modeling in agent-based modeling, where the modeling happens at the level of individual agents, in system dynamics modeling, you often think of groups of agents as one way to think of it, right? You have what's called a stock and you have a flow, and the stocks and flow tell how a group of individuals or resources change from one group to another. So in this case, you have a product adoption diagram going on, and you have potential adopters, and then you have actual adopters, and there's a transition between the two. Now, one of the big differences between systems dynamics modeling and agent-based modeling is the systems dynamic modeling is still fairly aggregated. So you're thinking about groups of potential adopters, right? You're not thinking about an individual adopter, right? And so as a result of that, it just takes a different modeling framework. And as you'll see, if you get to the section on why agent-based modeling, I think, you know, many of these platforms, systems dynamics, agent-based modeling, many of them could be used to answer the same questions, right? And really, the question you want to ask is, when is the representation of agent-based modeling appropriate for the question that I want to answer, right? So you could build almost this exact same model in agent-based modeling. In fact, I've built versions of this model in agent-based modeling, this new product diagram model, right? And it just depends on the question. Here, they're kind of just looking at the overall flow of potential adopters to adopters and what the effect of word of mouth is. But what if you want to know, for instance, who is the most influential person in this group of adopters, right? Who talks positively about this idea to other people? If you want to know like individual questions, then you're going to need an agent-based model, and this system dynamic model is not going to work as well for that. Okay, so that's what the difference is between agent-based modeling and system dynamics modeling. Now, Norman also asked what the how to integrate them. Well, one of the nice things is that there are ways to integrate them. So agent-based modeling, as I mentioned, does a much better job of modeling individual elements, whereas system dynamics modeling does a much better job of modeling aggregate elements. So for instance, if you think about something like a agricultural resource like grain or trees or something like that, a lot of times we're not interested in the individual tree or the individual piece of grain. We're interested in how much of that resource there is in general. But we might be interested in individual people living in a community that are dependent upon that resource. So what we could do is we could actually build an agent-based modeling the people and the individuals, a system dynamics model modeling the agricultural spaces, and then integrate them together. And in fact, NetLogo has a primitive or fairly good system dynamics modeling framework set up. And I won't talk about this officially in the course until much later, but for those of you who want to play around with it, if you go, let me share my screen again. If you go up to the tools menu bar of the system of NetLogo, and you go down to System Dynamics Modeler, and I think I have to share this screen separately, so hold on one second. You will get something that looks like this, right? And this is actually a fully working System Dynamics Modeler where you can draw stocks, you can give them labels like graphs, and I have to get an initial value, right? And you could build up a full system dynamics model in this way. And NetLogo actually has one model. It has a set of models, and let me go back to the other window. It's a little tricky, but let me go back to the other window. So NetLogo actually has a set of models that already are integrated. So if in the file, in the models library, if you go all the way down to the bottom of the sample models, there's a section called System Dynamics. And one of the System Dynamics models that I'd like to illustrate is the wolf-sheep predation model. And so this one, okay, is it showing up right? Yeah, kind of, okay. So this one will actually allow you to run both a system dynamics model and an agent-based model side by side, and then you can compare the two to each other. And so here I'm running a system dynamics model on the right, the aggregate model, and on the left I'm running the agent-based model. And one thing you might know is that the systems dynamic model continues to have wolf and sheep around all the time because of the fact that you can go to a very low population in a continuous aggregate model and still rebound, whereas in the agent-based model, because you eventually go down to just discrete individuals, the wolves in this case died out and the sheep took over the world. And this is something we'll talk about more when we get to why agent-based modeling is useful at different times. And just so you can see, the wolf sheep model has actually a systems dynamics implementation, right? And here's a full realization of it. And this is all in NetLogo. So this can actually feed directly into the model, right? And besides the wolf sheep model, you can also, besides having the models run simultaneously but separate from each other, you can also integrate them. So there is another model that's listed as unverified under System Dynamics called Tabanuco-Yagumo. And this model actually has a individual level model for trees, but then has a System Dynamics model for the tree growth rate, roughly. And so this actually integrates, oh, I gotta click over here. This actually integrates the individual level model with the agent-based model. So I highly recommend, I don't have time to go through the details of all these models, but I highly recommend, if you're interested in the integration of system dynamics and agent-based modeling, to spend some time exploring some of these models. So great question, Norman. Thank you very much for sending it in. Yeah, and I think that's it. So that's all the questions I had at this point that I think I've sent in. Let me double check the Twitter feed real quick. But yeah, it looks like that's it for now. Paula and Sebastian, did you have any more questions? Looks like you're working on one. So for the rest of the audience, just a quick recap again. Everything will be available after this is done. I will post a link. These videos, just because of the way Hangouts on Air works, actually get attached to my personal YouTube account, not to the Complexity Explorer account. So I'll post a link to it in the forums afterwards. It'll make it easier to find that way than trying to dig through my personal account and find it there. So I'll make sure it's up there afterwards. Okay, so Sebastian and Paula, I have another question. What's the difference between a model and an application, like a distributed algorithm? Is it difficult, useful to go from one to the other? So I guess a little bit, it depends upon what you mean by an application, right? I often think of an application in this case as a tool of some sort that you're going to maybe help use you to make a decision or to complete some sort of task. Is that kind of what you're thinking about, right? Okay, good. So I think that a model has a different goal, right? A model is often trying to describe a process, describe a phenomenon you see, right? And it can be used in an application, right? So you might build a model to help you make a decision, right? To help you support some other an application or an algorithm. But the goal of it is descriptive, as opposed to often applications, the goal is prescriptive or predictive, right, in some way, where you're trying to build something that's going to help you change the world, change the system that you're looking at, right? So this actually, probably the clearest way to explain this difference, right, is that there's actually another whole community that calls themselves autonomous agents and multi-agent systems, right? And they have a conference called AMOS every year. That is related to agent-based modeling, but often those researchers are studying how do we build an agent system to achieve a particular goal, right? So we want to put together a bunch of robots and we want them to swarm in a certain way, right? To follow a certain pattern, right? And a lot of times so their goal is more of a control or an engineering goal, right? As opposed to describing a system that occurs naturally in the real world, right? So I would say that's the big, to me, that's the big difference, right? One is I'm trying to describe the world around me. The other one is I'm trying to engineer some particular goal to occur, right? Now, is it difficult, useful to go from one to the other? Yes, I think it is, right? So in fact, in the section on social networks, in the complex modeling section, I think it's 1.5, right? I actually talk about some work I'm doing very recently where we model word of mouth influence in a social network, but then we build a decision tool around that model, right? To help us make decisions about what the efficacy, how well different policies would work in that space, right? So in this particular case, what we're interested in is trying to get people to convert to premium membership on an online, massively multiplayer online game, right? And so the question is, once we have a model of how people decide to convert, can we then ask questions about like, who should we provide an incentive to? Like maybe we give out a free virtual good or something like that to certain individuals to try and convince them to convert to premium membership. And then what would be the outcome of those goals? So in this case, we're going from a model that we built to understand the system to a decision tool, an application that will use that model to make decisions about the world, right? So I think often it is useful. I think it's also potentially difficult at times, depending upon what you're trying to do, right? If you go back to like the swarming case, right? It turns out it's very easy to come up with, well, not super easy, but it's at least we have models of swarming behavior in natural systems, but then trying to get writing control algorithms that try and get robots to swarm in similar ways has proven more difficult than we would have thought at times, right? And because of the fact that they actually have real world sensors and real world capabilities that don't work exactly right. And so we have to build in a lot of noise tolerance and things like that. So the Boyd's model, for instance, the flocking model we talked about right off the bat, that does great in virtual systems of simulating what things might look like. But once you move to real world systems, you have to build in a lot more things to control for how noisy your sensors are and how noisy your, what they call actuators, the things that actually move the robots around are, right? And so it can be more difficult than you might imagine at times. But yeah, great question, for sure. Anything else? See, nothing else coming on over the Twitter. Okay, and double check real quick in the forums to make sure nothing's going on there. So yeah, it looks pretty good. Okay, pull up the Q&A app. Okay. Do you guys have another question? Oh, you do. Okay. Don't feel like you have to type out quickly if you do. We'll probably will wrap up in the next 5 to 10 minutes or so, but yeah, okay. So Sebastian and Paula have another question. How does NetLogo behave with large models? Have you encountered any limits with it? So actually, that's a great question. As you'll see in the complex models section, you can go pretty big. And we've built models with tens of thousands and hundreds of thousands of agents before within them. It really depends upon a number of factors. It depends upon how complex the model is itself, right? How complex the decision making of the agents are, how complex the environment is, right? And kind of how quickly you want the results. Like when we're doing something on the order of say 100,000 to 1 million agents, we're often talking about letting the model run overnight, right? And things along those lines, right? The biggest limit you're going to run into is you're going to run into the memory size of your computer, right? So each agent, depending upon how big you've set it up, to how many properties it has, is going to take up a certain amount of memory in your computer. And after a certain limit, you might run into that space limitation, right? Where NetLogo just can't run the model because it's requesting too many agents. In reality, I rarely run close to those limits in most of the models that I build. A lot of people, so partially this is because I've been programming in NetLogo for almost 10 years at this point, right? And so I know, well, actually, wait, it's been longer than that. It's been almost 15 years at this point. And so I know the language pretty well, and I can often figure out how to make things run more efficiently. And throughout the rest of the course, hopefully I'll teach you guys some of those tricks, right, of how to make the code run better. NetLogo also has vastly improved recently, and by recently I mean within like the last 5 years, because now when you run experiments, it will try and determine if you have multiple cores on your machine. So each CPU now has multiple actual individual cores. And if you do have multiple cores, it will actually allocate that processing in a distributed fashion across those cores. So it will actually speed up quite a bit when you're running multiple experiments. And in fact, I will often, some of the models that I run, I will actually run in both a headless state, which means that the GUI, you won't ever see the graphical user interface. You can run it from a command line, which means it can run even more efficiently, because that means all that space that's used to display graphics to you is now not being used, and so you can run larger models and for longer periods of time and run it faster, right? And so that's one way to get it to do even bigger models. And then the last thing I'll mention is that you can actually have NetLogo kind of outsource some of its work. So NetLogo provides a number of extensions, and there's an R extension, which we'll talk about, a MATLAB extension, and some other things. So if there's some really complex modeling and you can't figure out how to do it in NetLogo, you can actually have NetLogo call a procedure in R or MATLAB or some of these other routines, and then run the computation in those routines. And I won't get into a lot of detail now. We'll talk about this at the very end of the course. But essentially, NetLogo supports 2 APIs, which are application programming interfaces that allow you to work with the NetLogo language from other places. One is what's called an extensions API. And so the extensions API allows you to wrap code around other software packages and then call those software packages from within NetLogo, right? And then the other one is a controlling API, and the controlling API allows other software packages to call NetLogo and make NetLogo do things, right? So between those two things, you can get fairly complex models to run. Okay. So yeah, great question though, and we'll talk about this in more detail as we keep going, for sure. Any other questions out there? Okay, just checking everything. I think that looks like it is it. So I want to thank Paula and Sebastian for being on the line today. That's great to have you guys there. And I want to thank everyone who submitted some questions ahead of time. I'll go ahead and stop the broadcast now, and it'll take me probably about 10-15 minutes to get it up on YouTube. But once it's up there, it will then be available for everyone in the course to see what's going on. And, by the way, feel free to give me, we've never done office hours this way before in the Complexity Explorer. We've usually done them in other means. So if you have any comments or feedbacks about the way this works, let me know. And I'm happy to take them into consideration, try other formats, try different ways of doing it. But I think this actually worked pretty well. So I'm excited to continue this way. Okay. So take care, everyone. I'll see you. Bye, Sebastian, Paula. Nice to see you again, and I'll see you guys in a week or so. Okay. Take care. Bye.